Good afternoon, everyone. I'm Mohammad Inzamamul Haq. I'm doing my master's in electrical engineering in Texas State University. Today, I'm going to talk about my paper, which is a facial expression recognition approach using deep convolutional neural network for children with autism spectrum disorder to identify emotions. The outline of my talk would be introduction, and then I'll talk about some related works, the computational resources I've used in this paper, the procedures, results and discussion, future work, and lastly, conclusion. So communication between human beings, there are two ways, verbal and non-verbal. Non-verbal communication types, there are different types such as facial expressions, gestures, eye contact, touch space, etc. Unlike other non-verbal communication, facial expressions are universal. So in 1971, Ekman and Friesen, they identified 6 facial expressions that are universal across all cultures. And those are anger, disgust, fear, happiness, sadness, and surprise. For children with autism spectrum disorder, face processing is a very challenging task. By 5 to 7 years, children with ASD, they can recognize happy and sad, but they have harder time with other expressions. Teenagers with ASD still are not that good to recognize fear, anger, surprise, disgust, these expressions, compared to developing teenagers without ASD. So in this paper, a novel idea is presented, which is to teach the young children with ASD to recognize human facial expressions in a friendly and practical environment. So what will be the end goal of this work? The end goal will be to make a mobile application that will correctly recognize and classify facial expressions in different lighting conditions from different viewpoints, and will display an emoticon of the corresponding recognized expression. So here is a very simple workflow diagram, as you can see. So the first task the app will do, it will open the camera. It can be any device with a camera, and it will open the camera and points the camera when the children will point the camera to a face. Then it will recognize the facial expression and it will show the expression with emoticons. So the main thing here is to correctly recognize facial expression. And what do we need for that? So we need datasets containing images of human faces of different expressions. We also need image processing, and I have used a deep convolutional neural network model as the algorithm. So the dataset that has been used in this paper is AFIR 2013 dataset from the famous Kaggle's Challenges in Representational Learning Facial Expression Recognition Challenge. So the data consists of 48 by 48 pixel grayscale images, and there are 7 categories. The 6 I already have talked about. Those are the 6 universal expression, and along with them there is another class which is the neutral class. So total of 7 categories. And the training set consists of 28,709 examples, and the validation and test sets contain equal number of images, which is 3,589. So various work has been done for young children with ASD in this field, facial expression recognition. One study suggests that slow dynamic presentations facilitate facial expression recognition by children with ASD. Another research implemented principal component analysis to identify the most feasible method for realization of a portable emotion detector for children with ASD. So all of these results show that children with ASD, they have very severe expression recognition deficits. So for this work, the work that has been done in this paper. All of the work has been done in this LEAP cluster. So this is a cluster of Texas State University, and as you can see, it has 120 compute nodes, 28 cores per nodes. It has 128 gigs of RAM per node, 400 gigs of Scratch, that is SSD per node. So the programming language that has been used is Python. We have used some packages such as Keras with TensorFlow backend, NumPy, scikit-learn, Matplotlib library. And for image processing, we have used OpenCV for Python. Moving on, why do I chose to go with deep learning instead of machine learning? So deep learning is easy to implement and it works faster. Why? Because in machine learning you have to have two separate algorithms for feature extraction and classification, whereas in deep learning with only one model you can do both of the feature extraction and classification. So with deep learning, the complexity of design is way more less than machine learning. So moving on, this is the DCNN model architecture that has been used in this paper. To better understanding it, I have tabulated this exact same model in the next slide. Here it is. So the input layer consists of 48 by 48 grayscale image and 1 because it's grayscale. So the full filter size that has been used here is 3 by 3. So we're using convolution and pooling layer, again convolution pooling layer, again convolution pooling layer, finally fully connected, and the softmax classifier. So you can see the output size of every convolution pooling layer and also the fully connected layers and also the filter and pool size here. So what does the convolution layer do? So it's the core building block of CNN. So the primary purpose of convolution layer is to extract features from input image. So it accepts images with some learnable filters and then outputs the activation maps as shown in the figure. So as you can see, it's just element by element multiplication. Then when we get those convolved feature, those activation maps, we run activation function on those, such as ReLU activation function. Here is, it can be shown that the ReLU activation function just accepts positive values, and whenever it gets some negative value, it replaces it with 0. So there are various activation functions. In this paper, I have used ReLU activation functions and also ELU activation functions for different experiments. So the pooling layer, the primary function of pooling layer is to progressively reduce the spatial size of the input volume. So doing this will allow us to reduce the amount of parameters and computations. And the fully connected layers, the name suggests that it is connected to the previous layer fully. So it is the standard for feed-forward neural network, and fully connected layers are always placed at the end of the network. And softmax classifier is our final layer, and it is actually the generalization of the binary form of logistic regressions, and it outputs probabilities for each class. So as you can see in this picture, the middle one, this one is the original picture from FER dataset, and with image processing by using OpenCV, I have created 4 other datasets from this original datasets with different lighting contrasts. So the most left one, it is the most darkest one, and so on. The most right one is the brightest version of the picture of the dataset. So with these 5 different datasets, I have tested my model to see how the model works for different lighting conditions. As you can see, this is the final results from our original dataset, and we got a validation accuracy of 64.88% and test accuracy of 63.11%. So in Kaggle's challenge, the leadership has 71% accuracy. So as an initial work of this project, 63.11% is not that bad. So you can see in the plot, I have plotted loss and accuracy, and for 100 epochs, and after 100 epochs it is pretty much stable. So 63.11% test accuracy for original dataset. And also I have tested the same model for different lighting conditions. As I have mentioned, I have 4 different lighting dataset, and for each of those I have similar graph. I won't show them, I will show you the comparison for test accuracies with different datasets. So the left one here is the original dataset, which is 63.11%. As you can see, from the darker dataset I get 53.10% test accuracy. From the darkest one I get 46.46% test accuracy. From the brighter dataset I get 59.65%, and from the brightest dataset I get 58.37% test accuracy. So from this plot I can conclude that the model is having trouble with darker and darkest pictures. So in the future work, I'd like to improve the model's performance for different lighting conditions. I will train and test with datasets from different angles so that the model, the final app, can recognize human facial expressions from different angles and from in different lighting conditions. And also to build a simple app, which is also the future work, to open the camera and show the facial expression of the person with an emoticon. That is eventually our end goal. So the goal was to design a deep neural network for facial expression recognition that can help children with ASD to recognize emotions. Different approaches are being considered for a better model which can recognize dark and bright images, as well as improve the test accuracy. And this AFIR dataset was used for validation and testing. And finally, we compared different datasets with different lighting conditions to better understanding the model performance. Thank you.